Hello everybody, today I'm going to analyze the problem related to dynamic programming. We are given several boxes with different colors represented by different positive numbers. You may experience several rounds in removing boxes until there is no box left, and each time we can get some points for removing continuous boxes of the same color. Return the maximum points you can get. This is interesting problem. There are reach for possible ways to solve it, but as usual, first of all, let's consider brute force approach. Brute force approach is very easy to implement here, and it's not surprising because the idea in most cases lays on the surface, and it's usually the simulation of process which solves the problem. For example, in this case, this process is the sequence of reducing operations, which means either the merging of similar boxes or merging some separate boxes. There are no hints and preferences which box we should start this process from, so this means we have to investigate all possible sequences of merge operations, of removing operations. For example, we can remove 3 boxes with color 2 and we can get 9 points from this. We can remove either 1 box 4 or we can remove 3 boxes. In each case we can gain different number of points, and it's not clear how to find the optimal way. That's why we have to investigate all possible sequences of removing operations. Now, how we can improve this procedure? The approach I'm going to describe in a moment is called dynamic programming. It's used and known widely, and I will drop the details about what it is. In short, this is a technique to reduce the initial problem to the similar one but smaller and simpler, both in scale and structure. For example, in this case we can introduce some magical function. We're not interested at the moment how exactly it works, hence the name of this function. Let's call it again. This function automatically calculates the maximum gain for the specific range of boxes, for the specific range of sequential boxes to be exact. In this case, it's easy to see we can reduce the original problem to these small ones. In this case, we are merging 2 sequences separately, and the second sequence is consistent from just 1 box. This is a more complex case. In this case, we are trying to group some boxes of the same color together and merge them together. In this case, we can get more points, and it's easy to see that in the process we have to merge or to remove intermediate boxes. And in this case, once again, we can use our magical function to do this job. And yeah, the idea is clear. These both cases can give us the complete solution. Let's call it. First of all, we have to measure the length of our original array of boxes. And then we have to invoke our magical function. Let's call it gain. So this function returns the maximum number of points we can get from the given sequence. This sequence is defined by the left and right edge. These edges are defined by I and j indexes respectively. Also, we have to introduce auxiliary function square, which returns the square of some value. Next, we are processing edge cases. It's a trivial task. Okay, and now we have to implement our two cases we discussed earlier. First of all, we have to find the color of last box in the given sequence. And next we can calculate the base gain, the initial gain we can get from merging this last box separately from all the rest boxes. This job can be done by invoking our magical function on the first part of our sequence and adding the number of points we can get from the merging the tail of this sequence. And in order to code the second case, we have to find the boxes which have the same color as the last one. In our sequence, we're interested only in boxes of the same color, hence we have to add the if construct, the if clause, and the answer to our question is going to be the maximum of already calculated gain and the newly one. And the new gain we can calculate splitting our original array into chunks and merging them together separately. In this case, we are interested to group the boxes of the same color together and removing them together. In this case, we can get more points, and potentially we can improve the total gain in this way. Okay, looks good. Let's check the solution of test input. Okay, it works. Now, before going further, we can optimize our solution by introducing the caching of already calculated results. This will allow us to avoid repeated calculations. This technique is called memoization or caching. We have to introduce cache for all possible inputs of our function, and instead of performing calculations from scratch, we can use cached results. It's easy to see that the time complexity of our solution is going to be big O of n cube, because in worst case scenario we have to calculate the values for all cells in our cache. And this means we have to invoke the gain function at least n cube times. Of course, the solution is much better than the brute force one. Brute force approach has the time complexity big O of n factorial. Now we are returning the cache results if we calculated it earlier, and now we have to preserve the calculated results into cache, and this finalizes the solution. Let's check on test input. Okay, and let's check all test cases. It works, and as you can see, it's a quite decent solution. That's all for today. Thank you.